first of all, like I'm also doing the deep learning research, right? So my experience for doing deep learning research in academia, I summarize it into we need a 4G. The first G, we need a grant, right? So of course, right, we need a grant, right? No grant, you cannot carry out the research, right? Second G is GPU, right? We need a H100, V100, all the GPUs, right? We cannot compete with Meta or Google, which they have 10,000 of GPUs, right? But we only have like 1 or 2, right? A third one, we need graduate students, right? Of course, right? We need graduate or postdoc or undergrad students to carry out the research, right? We need talent. The last one is gradient descent, right? Almost everybody doing gradient descent, right? So you cannot avoid it, right? So that's why today I want to just focus on the last G, right? I want to talk about the stochastic gradient, right? And I want to using the stochastic gradient to carry out, to be able to do the uncertain quantification. So yeah, so that's why I'm going to focus on, I will not talk about ping or deep net, anything. I will talk about, focus on, stochastic gradient. So this picture basically showing you is a UNet structure. So what I did is instead of just input output doing a point-wise estimation, so my UNet structure give you 2 outputs. One is the mean prediction, the other is quantify the confidence interval, basically give you the standard deviation or variance prediction. So that way you just one input give you 2. So you know the confidence interval, everything give you the uncertain quantification. So here's a picture of the 4 waves of AI. So basically showing you the different stage. So this is basically a DARPA. They have this roadmap about this, the mapping to 4 different waves. So the first wave from 70 to 90, the typical is the deep blue, they play the chess, right? The second one is the AlphaGo. The second wave from 2000 to the present, right? You have the autonomous driving, right? So the Go, AlphaGo, right? The third wave is like from 2020 to 30. That's basically doing the contextual adaptation, so right now we are experienced about transformers, right? Large language model, or like AGI will be the fourth wave, right? From 30, maybe will come a few years earlier, right? So that's about AGI have this artificial general intelligence. They are possible. Okay, so I think this roadmap is pretty accurate. I think they did it in 90s, so that they project in a pretty nice way. But there's some challenge, so that's why I want to go through with you. The first is the loss landscape of the modern deep neural network, right? So if you look at this is basically a visualization of the loss landscape of the deep neural network. So let me show you a movie. This is a movie. Let me show you. So this is the gradient descent. It starts on the top. You want to find this green area. This is the deep of the valley. But however, you're going to stuck in the middle. That is because there's a lot of local minimum there. You're going to stuck there, right? Because you don't have really a global picture, where is the global minimum is, right? So that's what we are facing the challenge, because the landscape is too rough, and our gradient is strongly non-convex, right? We don't have a very good optimization algorithm can guarantee you to find the global minimum in the non-convex setting. Right, so that's a challenge. Why we think about the deep learning, the training is so difficult, right? And become chemistry, right? So that's become challenge, right? So that's why it's difficult. So today I'm going to talk about scalable training, right? How to training a large-scale deep neural network, right? So this is also the motivation, right? So remember I talked about so as a proof mathematician, right? We don't have a lot of GPUs. Right, so then how can we train efficiently, right, on training larger scale deep neural network, right? So that becomes a challenge, right? And we have to improve the algorithm because we cannot buy enough GPUs, right? So then only thing we can do to improve our algorithm. So that's why today's talk I'm going to talk about how to enable fast training of a large scale neural network, and also talk about how to quantify the uncertainty in deep learning. So this is one of the papers we developed. It's called adaptive empirical Bayesian method for sparse learning. So in particular, along this line, we developed a few algorithms. So I'm going to talk. The first one is called stochastic gradient Monte Carlo. So this is joint work with my students and my postdoc and my collaborator, Fan Liang. So let's look at some notations. The first notation is let's assume the data set we call capital D. The mini batch are called lowercase d, right? Just a mini batch data in the whole data set. The mini batch, so we have the model parameter, I call it beta. Then, because I want to do in a Bayesian way, so we do the log posterior density estimation. So that's, I have the log posterior likelihood approximation, right? So that's the typical log likelihood. Then I will have this stochastic gradient descent using a mini batch because I cannot afford to load all the whole data set into the GPU, so only can take a mini batch, sort it in. So that's why my likelihood will be L tilde. The tilde means the mini batch data. So the last line represents the mini batch representations. Okay, so that's the setting, very similar to gradient descent, but just in a Bayesian setting here. So everybody using stochastic gradient descent, right? That's like the golden standard here. So why it is good? Because the stochastic gradient descent update the parameter using the mini batch approximate, right? The likelihood. So basically, using funded map for model parameters through the stochastic optimization. And the drawback is cannot capture the parameter uncertainty and that can potentially overfit the data, right? So that's the challenge. So how to avoid that challenge, right? So that's why we try to introduce the Langevin dynamic and the stochastic gradient Langevin dynamic. So the idea is we try to introduce the Langevin diffusion with the distributed distribution. And described by a stochastic differential equation, right? We're just introducing a noise term, right? This W represents a Brownian motion. And then we just discrete in time, right? We're using Euler method, right? Then we can have these finite difference representations. Then we sample the Brownian motion using the Gaussian distribution to sample it. So then the theory can prove that it's a symptotic convergence to the original distribution here. And this tau represents this basically the kind of temperature, right? So the solution tends to the global optimum with a high probability. So that's the Langevin dynamic setting. So the advantage of the stochastic gradient Langevin dynamic is we can sample the neural network posterior distribution, right? So that's why I can model the uncertainty. And also I can compute the posterior expectation to obtain more robust result, right? Because I can get the mean instead of just the peak. And what if you have multi-model, right? If you only can compute one peak, it may not be the global optimal choice, right? So that's why. And also it can escape the local optimals to achieve better point estimations. So the SGLD update all parameter with the same step size, and this could cause the slow mixing when you try to update the parameters, right? So that's the drawback of the SGLD. So that's why later on we developed so-called preconditioners. So the preconditioner can take care of update each parameter with their own step size. So that's what we later on developed. So that's why we have this MCMC is also the standard when you do sampling, right? So UQ is kind of critical for AI safety problems and also reinforced learning, right? So the MCMC is the golden standard, right? Which is known, it can handle multi-model sampling, right? It can accurately predict the confidence interval. Also, it can apply to the non-convex optimization, give you the better point estimate. But however, this one does not take advantage of the gradient information. So that's why we want to improve this MCMC to enable consider the gradient information. So that's why we developed the tool that's able to handle the gradient information. Okay. So here, let's say, so that's why we're introducing the Langevin diffusion. Langevin consider the gradient information, so that's the gradient U in the front, right? And also, we can change the temperature, right? The temperature, we can use in different temperature. It will give you different, the distributions, right? So that's why you say if I make the tau smaller, right, it can give you the peak, right? That's why you remember if you do the optimization, there's a simulated annealing, right? The simulator plays that trick so that they change the temperature, so can the peak, you can have high probability to sample, the peak values. So that's a similar setting, right? This is you can change the temperature. So that's why we're introducing this stochastic gradient Langevin, dynamics. So I already talked about. So you can update the parameters, right? Very similar to gradient descent, but you add this noisy term, right? So that it will converge to the Gibbs distribution. So that's the setting. So that's the first paper, I think, is the Max Welling, right? He's currently work for the Microsoft. Okay, so now let's look at what the stochastic gradient can do for you. So this is a simulation. So I have 9 local minimum. The middle one is the global minimum, right? I can run the stochastic gradient Langevin dynamic. I try to find the global minimum. Theoretically, SGLD will guarantee you go to the local minimum, the global minimum, but just take it forever. So let me show you a movie here. So if you see, this is I'm doing sampling. First the track on this top local minimum, right? You can see these iterations, right? It slowly will go to the next one and go to the next one. Eventually will go there, but it take over 1 million times. It's just very slow. You say you jump to the next one, right? It will jump to another one, local minimum, okay? It's just very slow. So if you want to do the climate prediction or very expensive models, it should take forever, all right, for you to converge to the global minimum. It's not practical in the real world application. Okay, so that's why you can say it will reach 1 million easily, okay? But it just not go to, it's just trapped in one place for a long time before it escape to another one because of the energy well, trapping there. So that's why this introduces us to think about how to accelerate the MCMC. So that's why in 1983, this is the famous simulated annealing, right? Today I'm going to talk about the so-called replica exchange MCMC. It's old method. It's not new, right? It's 86, okay? So we try to say, okay, let's just try to do this replica exchange applied to deep learning, right? It's a neural network. We think it's a very straightforward apply the replica MCMC applied to neural network. We're going to have a paper, okay? So that's the issue we thought. It should be easy paper. So that's why we developed this so-called replica exchange SGLD, published SML 2020. So let's look at the setting. The idea is I want to do, instead of one MCMC, I'm going to have 2 Markov chain, okay, run in parallel, the exchange information. And so have top one, the first chain has a higher temperature than the second one. Second one will run with lower temperature. Then these 2 particles going to swamp their probability with a probability rate. So this is how they exchange, this is the exchange rate, okay, how they exchange information, okay. And this is, in other words, this will be a jump process including a macro process, okay. This is just 86 stuff, okay, it's not new, nothing new. We think we can just apply this, right, to neural network. So philosophically, how it works, let me explain to you. So think about you have, this is a big valley, the Grand Canyon, okay? And you run 2 teams. One team run helicopter, we call the exploration, right? If the helicopter finds a good place, good spot, say, this place might have the global minimum, right? Then they send a lot of local troops, okay? Go there, okay, hike there, down the valley, find the global minimum. So the idea is gonna easier, for you just blindly to go into the valley, find the global minimum, right? Because I have a helicopter searching the spot, right? Then I send several local team there, right? So that's why we have so-called exploration and exploitation, right? We have 2 different color. Red means high temperature. The blue means lower temperature. The high temperature help you fast explore the whole area. But the lower temperature help you, using smaller step, go finding the exact global minimum. So that's the basic idea. So then they exchange information, right? They communicate with the local team, right? So that's how this idea works. So initially we thought just, easy 86 idea, apply, neural network, it works. But it turns out it doesn't work. Let me show you why it doesn't work, okay? So the reason it doesn't work is because we are using a mini batch, right? We are not using the whole data set. If we are using the whole data set, problem solved. But however, in the current world, you cannot load the whole data set in one gradient descent, right? You always cut the data into pieces. The mini batch will cause noise and bias. And that gives us a big trouble. We cannot converge. So that's the problem. So that's why we have to correct the swamping rate. So that's why we're running you say I always put the tutor there because I'm running the mini batch. That exchanges the information between the 2 mini batch. And because of the noise, the cause of the trouble, so that's why, when you're using the traditional 86, their swamping rate, it's gonna give you the problem because it causes a large bias. So that's why we have to find a new way to improve, not using the naive swapping rate, have to use a corrected swapping rate. So that's why we have to come up with a correct algorithm. So in this correct algorithm, we have this suggested unbiased swapping rate, consider this noise, right, introducing from the mini batch data. Okay, and also it depends on the temperature you set up for these two Markov chain, right? So you cannot, so depending on how you set up the high temperature, low temperature, right? So that different temperature will give you different correction of the swapping rate, right? So that's why we have to come up with this unbiased swapping rate, particularly for the mini batch setting. So then we can using that to swapping of these two chains. Okay, so that's the basic idea. So let me show you. Yes, go ahead.
I wonder if, do you assume L, the loss function, in terms of beta, satisfy log concave or log topography or something? Do you have any assumption about L?
The law. This is just this is we don't assume. No, this is just like typical Monte Carlo. Yeah. So let me show you what happens in these two. Do a side-by-side comparison. So the left doing the SGLD, the middle is a replica chain. You see, just like 2,000 iteration is going to reach already the global minimum. Okay, so much faster. Compare this, take a million. This you can see the path. You can see this is just like exchange information, the path. So they can explore this 9 minimum very quickly instead of this one take forever. Although theoretically going to converge, but it's just very slow. Okay, so this is just this replica change ideas. I'm going to show you. So let's look at I want to compare this stochastic gradient longitude versus the replica change. So this is the acceleration we obtained in the rate in the versus 10 norm. So you can this is the acceleration. The k is basically the swapping divided by the iteration. Okay. So now the question is, can we do better than what we currently do? So the idea that's come up with our second, in another year, we developed so-called exponential acceleration via the variance reduction. So published SAR 2021. So the idea is, in the original, the energy estimation, right? So everything comes from the desire to obtain these effective swapping drivers to design more efficient energy estimation. So everything come up with whether you have a good estimation of the energy, right? But however, we are experiencing a very local mini batch, right? You have only very small set of noisy data, right? And the energy we estimate are not good at all, right? So that's a problem. And if your energy is wrong, then your swapping rate, everything will be not correctly. So that's why the core concept is how to reduce the variance and have a good estimation of the energy. So that's why we're using, this is called variance reduction technology. So basically try to come up with a better estimation. So this is so-called the control variate, right? It's a very classical variance reduction technique we try to apply here, try to estimate the variance using a local approximation, right? So that's why this is C is so-called control variate constant, okay? So if you're using control variate, you can get a so-called C star. The C star will be the optimum one, right? And here you think about you using you basically do estimation, right? You basically collect whatever your local, information. You sum them up. You do a energy estimation of this information you can get. You update it. Then you reduce the variance, right? Then this is just a control variate setting. Okay, so that's the basic setting. And based on that, we can, have an unbiased estimation, for the variance reduction. So then we can decompose this variance, right? This is just a, control variate setting, right? So we try to compute this so-called C star. So the idea is we just need to calculate the covariance function, right, between this with the local information you collect. Then you divide the variance. So this is the C star is the optimum, control variate constant. Then you compute this, you update the information. So that's we can do accelerate the convergence. So then this is just the algorithm, right? We basically propose this correlate beta hat. Then we try to compute the optimal C is unknown. Then if you can set the C equal to -1, or you just using the adaptive C to using control variate to update it. Okay. And we have lemma to prove this variance reduction energy estimator is this is the arrow, right? This is the total number of samples. This is the local mini batch. This M is how many steps you're gonna calculate the variance, right? That you do variance reduction. Okay, so this is just the error estimation. In the meantime, so for a smaller, right, variance implies more effective swamp. So you can use in smaller. There's a variance. Basically, we have this variance reduction for larger swamping rate. So this is an approximation of if you're doing this is N is the local mini batch, right? So you can do this swamping of beta 1, beta 2, exchange the energy estimate of the variance reduction. So let me show you. So this is what you can gain by doing this accelerated variance reduction technique. So this is a gradient descent. This is replica change. This is a variance reduction. So you can get a further acceleration using this technique. So we run a few tests. So this one basically showing you the simulation. We run is doing some kernel density estimation of the parameter. This is beta 1, so which is a trace plot of the MCMC. And so then we also have the sensitivity study for the variance. And this is basically the path of the log of the variance. And this is contour of the log of the variance. Okay. And so this plot basically showing you the convergence of test on the CFA 10, CFA 100. So this is basically the two color means this is basically you exchange information on infinity length. It's basically you don't exchange information, right? So it's not good, right? If you exchange information at every 50 step, you're gonna reduce the variance, right? This is basically showing you as long as you make the M smaller, you're gonna have better variance reduction. But there's nothing free. It comes with a cost, right? Because every 50 step you have to stop. You have to collect all the information. You calculate the variance. You update it, right? They run it again, right? So every time you have to do that, as long as you do it more frequently, you get a further variance reduction. But the computation cost is going to increase. Okay, so this is basically showing you that. Okay, so this is basically showing you the our method so can achieve the smallest error in the CFA 10, also the CFA 100 in the error plot. So that's that. And then this is basically for the larger data set. We run for CFA 100, right? And so you can see for a larger one, so we can have the further this reduction in the variance. Okay, so that's a variance reduction. So let me give a brief summary. So we run this replica change. Just look at the MCMC. We can show potential in exponential acceleration, right? The convergence in the non-convex learning. And we also did this variance reduction of the energy estimates, right? That give you the exponential more effective swamp. It can further accelerate the exponential convergence in the non-convex learning. And finally, so this is the first work we did do the variance reduction on energy estimate in the deep learning, right? So that can help us on the Stochastic gradient MCMC in the non-convex setting. So here's some papers, right? So we did on this non-convex setting to accelerate the convergence. The last part I want to talk a little bit about we did on the Bayesian sparse learning with the preconditioned SGLD. So I already talked about gradient descent, right? So now I'm going to talk about, so can we do preconditioning, right, on top of the gradient descent so that every parameter will have the own pace, own rate. So that will give you some further acceleration. So that's what we did here. So very similar setting, right? We do the Langevin dynamics, right? Using like the SDE, then we do Langevin dynamics. So what we did is we designed a preconditioned SGLD. The idea is we can update the parameter with different size, adapt to local geometry, and the resulting fast convergence for computing the beta, so that they have different scales. So let me show you some example, right? So this is I applied to the residual network compression. So the idea is we want to make sure, because think about in the neural network, right? We have millions of parameters, right? A lot of garbage, a lot of carry very small weights, are not very meaningful. So also it takes a lot of computational power, right? So as a poor mathematician, right, I only have like one GPU, right? So I cannot afford to run many. So what we do is we did a sparse neural network, right? I encourage sparsity so that I can get rid of a lot of weights, right? Let them to be 0. So I only have some meaningful weights left. So that's why I'm showing you here. So I can achieve, on the CFA 10, I can achieve 90% compression, right? So that I still can achieve 91.68 accuracy, right? With 90% compression. Still basically the same as your like a 30 compression, right? So this is the state of art, right? We can only need 27K parameters compared to the state of art, right? That they need 47K, right? For the state of art is 91.48% accuracy. We can beat them, and with half of the parameters, right? So this is showing you, right? We can have a much smaller network size, have better accuracy, can run with just one GPU instead of many GPUs. Okay, so that's maybe one way for poor mathematician to survive in the deep learning community, right? So that's one way. Okay. So now let's talk about the multi-scale flow, right? This is the one page I have the equations. So then let's look at the flow equation, right? We want to solve this flow equation. This is it's a lot of petroleum industry using that equation as well, right? So I think we do solving the flow equation, right? You need to solve elliptic equation coupling, right? This kappa represents the permitted field of heterogeneous permitted field, right? If you knowing that we can use a mixed finite element, right, that conserve the mass, right? So in the finite element, you need to using the RT0, right? Basically using RT element, that using the lowest order, and for the pressure, you use P0 piecewise constant element, right? Then, so the difficulty is the assembled matrix, the AH is very large and also heterogeneous, right? And it also depends on the kappa, right? So when you try to apply to different permitted field, it becomes a challenge. So that's why the neural network might have some potential to help us, right? So that's why we developed this problem. We try to mimic the multi-grid, right, and the multi-scale finite element. So that's why we have this upscaling and downscaling mapping. So think about here is the kappa, the permitted field. Then we have to run through upscaling, do the convolution, pooling, flattening, and the dense layer that we reshape. So then this is the idea is we want to reduce, right, do some upscaling, right, reduce the complexity and the degree of freedom, so that we can run a coarse grid solver, right, in this convolution layer, right. Once we solve it, then we can do this downscaling, make the dense layer again to reshape to the velocity field U and V. So the idea is I want to do the convolution in the coarse grid, so that can make a prediction, then I do the downscaling. Right? So this is the idea, also can help us to achieve some compression. So let me show you some numerical results. So this is, we can compress, so this is the dense layer. You need 6 million of the parameters, right? So before it's impressive, but now it's not, okay? So, but still you need 6 million, right? But however, if we compress it to like 70%, we just need 10% of the weights, okay? But we can achieve better accuracy compared to this dense grid. And this is just KRE, means kind of like representations, right, with different degree of freedoms, okay? The larger the number means the larger complexity of the problem. So you can see we can achieve 70% of the compression, right? Basically 10% of the weights, but we can achieve better accuracy. Let me show you the convergence, right? If I using the preconditional word, so this yellow color is our method. Basically, we're doing the precondition. It has less oscillation and it's much faster convergence on these 3 settings. And interestingly, if you look at the permeability field, right? So the left is true, okay? So this is the velocity x and velocity y, u and v. This is true. And this is the middle one using precondition. On the right, if you don't use precondition, you update parameter using the same step. And you can say because you use the same step, you cannot capture the local feature, right? So that's why you say it's a smeared. It's like the diffusion model, right? You diffuse the way, right? But if you have the precondition, you can capture the local features. So this is the 32 degree of freedom. Then we can increase the complexity. So you can see this have more features, right? So the same thing happened. So this is true, right? This is with preconditions, and this is without precondition, okay? I can even make it even harder. So you say this is a 128, so you can say this is true. this precondition, and then you can see without precondition, totally become white noise, right? This is basically showing you it's important to do some preconditioning during the step you have to carefully choose for each different parameters. So that's why I want to have a summary. So we propose this new adaptive stochastic gradient MCMC framework, right, that can pave the convergence and the minor assumptions. So the idea we do that is it's very difficult to prove convergence for non-convex normalization, right? But however, if I change the problem, become a sampling problem, then in the statistics community, there's a lot of tools I can use here. So my toolbox has much tools on MCMC, all these tools I can use, right? There's not many tools on non-convex optimization can help you. So that's why I go that way around, try to using this Bayesian approach, right, to basically learn a class of these hierarchical Bayesian models to help to do this data-driven adaptive penalty, and also eventually I want to achieve this a sparse neural network that's going to help me to run a smaller size of neural network so that I can run on smaller GPUs. And also, because I have less number of weights, right, it will give me more interpretability. I know what is the physical meaning behind it, right? I know, give me a lot of information than just blindly using just a huge, humongous number of weights. It's also more robust, right? Because if you have some noise, it may lead to another prediction, right? So smaller size will give you a more robust prediction. So thanks for your attention. So I'll take some questions now. Okay.